Our next speaker is Gleb Nenashev, who is going to be speaking on the maximum multiplicity of a generator in a reduced word. Gleb, пожалуйста.
Thank you for introduction, and thank you for this great opportunity. That's at Zoom, but it's still great opportunity. Okay, today, so yes, it's a joint work with a lot of people. It's Iba, Christian, Paco, and Alexander Postnikov. So we did this work maybe 2 years ago at MIT. We started this work, and now we almost finished. Okay, so the title is what we are doing. So the maximum multiplicity of a generator. Okay, and here's the first slide and definition. So we consider reduced words of maximum of longest permutation in Sn, and let mkn be the maximum possible number of sk in reduced words. And for example, M14 is 3. We need just consider this reduced word. It's maximal for 1,4. For 2,4, we can consider this reduced word. It's also 3. And M34 is also 3. We consider this reduced word, and it's maximal. In general, these numbers are distant. And for example, for when n is 5, we have 1, 5, 2, 5, 3, 5, and 4, 5. And these numbers are 4, 5, 5, 4. And it's not special situation that this is symmetric. Because if we consider, usually we will work with wiring diagrams. And if we consider wiring diagram, here we have 1, 3, etc. n. And in another end, we have n and -1 and 1. And we have some wiring diagram. And when we consider symmetric wiring diagram, just mirror of this, we see that number of sk will be equal to number of Sn minus k. Therefore, first proposition is mkn is equal to mn minus kn.
Gleb?
Yes?
There was a question in the chat. Randy Hood asked, could you please remind us the definition of a reduced word?
Okay, yes, of course. So for this talk, instead of reduced word, it's better think about wiring diagrams. And we have such diagrams. In each step, we have either cross or all wires go next. So, so for example, this is a reduced wiring diagram. And in general, we can write any permutation as product of simple transpositions. And we can write maximal permutation as product of n choose 2 simple transpositions in some way. Because n choose 2 is the length of maximal of longest permutation. And length is the number of inversions. But usually we will have such pictures, and main conditions that any wires, for any 2 wires, we have exactly 1 crossing. So here we have 1 cross. For these 2 wires, we have only 1 cross. Okay, and we count MKN, it means that we count number of crossing on level K. So it's first level, it's second level. Here we see that M23 is at least 2, and M13 is at least 2, and M23 is at least 1. And if we consider another wiring diagram, we have that this number is at least 1, and this is at least 2. And for this case, both numbers are 2. Okay. And it's first proposition, and second proposition that MKN is at most K times N minus K. How we can this proposition? Just consider large wiring diagram. And let's move to a few slides before. For example, we have 1, 2, 3, 4, 5, 6. And here we have in another direction. And it's a third level. We want to count M3, 6. And what we can see, that here, sum of these indexes is 1 plus 2 plus 3. Sum of these 3 indexes. And here, sum of indexes is 4 plus 5 plus 6. And in general, for MKN, sum of these indexes is 1 plus 2 plus K. And for these indexes, we need to consider maximal, maximal K wires, and it will be N minus K plus 1. And after each crossing on level K, sum of first K wires, of top K wires, increasing at least by 1. Here is sum 6, here is sum 7, here is 8, and etc. And therefore, we have at least, at most difference, the number of appearance of SK is at most a difference of these two numbers, and it's exactly K times N minus K. And it's the idea how to prove a second proposition. Let's go back. Okay, so we have this proposition. And someone can think that this number is unimodular when N is fixed. And it's almost true, but it's false still. So if we fix N, we have such sequence, and it's not unimodular in general. For example, if you consider such for N equals 12. For 12, we have 11, 15, 17, 18, 19, again 18, next number is 19. So it's not unimodular, but it's still almost unimodular, but I don't know how to formulate this, especially when N goes to large. At the beginning, it's increasing, and at the end, it's decreasing, but we can have some problems in the middle. Okay, but we can also see that this is not K times N minus K. It's 18, and K times N minus K is 36 here. So we have better bounds. We have better upper bound, and it's our bound. And why we have this bound? Because when we consider level K and some intersections on level K in wiring diagram, we can consider yi when yi is smallest y in intersection. So we have yi in few places. And in bound k n minus k, we always add, we say that we add at least 1 to the sum. And if we have, if here we have yi plus 1, we add 1 to the sum of top k y's. But we cannot have I plus 1 here, I plus 1 here, I plus 1 here. So in best case, we have I plus 1 here, I plus 2 here, and I plus 3 here. And if you did this carefully, you will get this bound. Of course, without missing steps. And this bound is almost this bound. So maybe it's better to think about this square root of 2k times n. So it's not linear on k. And for first 3 special cases, we have following formulas. M1n is always n minus 1. It's 1 times n minus 1. For this case, it's we have very good equality. But for k equals 2, we have this formula. And for k equals 3, we have this formula. Okay, for other k, we don't have formulas, but let's think a bit about one relation. And it's an idea how we found these formulas. We say that a sequence of subsets is a monotone weakly separated path if 2 sets different by 1 element. So we from A0 to A1, we delete 1 element and add 1 element. And also we need that minimal element from AI set minus AJ is at least maximal element of AJ set minus AI. Okay, and here's example of weakly separated path. It's exactly these sets. Okay, and in general, it's all methods how we can get a weakly separated path. So if SI1 SIL is a reduced word, then PK, this path of these sets is a monotone weakly separated path. And in a reverse direction, if P starts from set 1 to etc. k, then there is such a reduced word, such that pk of this reduced word is p. So just in some sense, it's a reformulation of problem, and it's a very useful method to construct examples. And of course, weakly separated sets are well studied for non-negative Grassmannian and such stuff. Okay, and our maybe main notation for this topic is a number ck, which is limit of mkn over n. And in previous example, so we have that C1 is 1, C2 is 3 over 2, and C3 is 11 over 6. And theorem that CK exists for any K. So this is well defined. And it's very fast. So it's very fast to present proof of this. So I will do it. At first, we know that mkn over n is bounded. Second property is mkn is less or equal mkm when n is less or equal to m. So this property is very simple. And third property which we need is this. It's also not hard to prove. And from these 3 properties, properties, we can prove our bounds. From second and third, we get that MKM is at least M over N, floor of this fraction times MKN. And from this, we just we just consider this, divide everything by M. And what we can see, if we fix N and K and M goes to infinity, this product tends to 1. So we get that any accumulation point of sequence MKM over M is at least MKN over N, any accumulation point. And from this, we immediately get that we have at most 1 accumulation point. And since we know that this sequence is also bounded, we have exactly 1 accumulation point. And it's a limit, of course. But it's existence, and it's not everything. The main result is that CK, in fact, is a rational number. And MKN is a periodic function where this part is always negative. So MKN is equal rational times N minus some periodic function. And of course, I don't have time to present proof of this fact. And idea is very technical. We just consider some reduced wiring diagrams in another sense, and we prove that there's only finitely many different combinatorics, and from this we get that this limit should be rational. Okay, and here's another problem, which is closely related to this. So if we can, it's a K-sets problem. We have n points on plane, and what is K-set? It just, if we can write, if we can draw this line, this is 2 set. If we can separate these 2 points from other 4 points, then this is a 2 set. For example, these 2 points are not 2 set because we cannot separate them from other points. And in 70s, was started, Lowish and company started to study problem about maximal number of K-sets for n points. So of course, for different configurations of points, we have different number of K-sets. And they studied a maximal number of K-sets. And our problem is very related to this problem, because at first, let's consider dual problem. And for dual problem, we have n, instead n points, we have n lines. N lines. For example, here we have n line. And later we have h of these regions. For example, we start here, we have h0. For this, we have 1. For next, we have 2. And here is 3. And question, maximize the number of regions of hk. Okay. And it's still not our problem. But if we change arrangement of n straight lines to pseudo lines, it's very similar. So now we have n pseudo lines and similar problem, for example. So, and arrangement on of n pseudo lines, we just draw some pseudo lines such that any pair has exactly one intersection. And we have still here, for example, 0, 1, 1, 2, 2, 2, 3. It's not very good example, but okay. Still we have such problem. And this problem is almost what we did. Here we have number mk and bar. And mk and bar be the maximum possible number of total appearance of sk and sn minus k in a reduced word of maximal of longest permutation. Just we consider two generators now, sk and sn minus k. But it's not big difference because in asymptotic sense, it's exactly same problem. If we consider this limit, so it's still well defined and it's same limit. So for this problem, limit is equal to problem to limit from previous problem. So, and if you're interested only in asymptotics, so it's you don't have any difference to study m bar or m. So it's they have same asymptotics. Okay, and another natural question. It's similar problem for minimization. So what we have if we minimize number of this generator. So the minimum number of Si in a reduced word is always I or n minus I, the minimal number from I and n minus I. So it's not very interesting problem for type A, but for other types, it's a bit more interesting. For type Bn, the minimal numbers are here. If you know what is Coxeter groups, you can understand it. Otherwise, it's not very important because it's only for this part. Okay, so for type Bn, we have these numbers, and now you see that we have 2, and in our original problem we have for type A we have 1, 2, 3, but here we start 2, 3, 4, and another end we have n, and for type A we have still 1 in another end. For type D we have this picture, and for E6, E7, and E8 we have these examples, and of course for other finite types we also check this. Okay, so thank you.
Okay, spasiba. Let's give Glenn a round of applause for a very interesting talk. Are there questions?
Yeah, I have a question. So are there any connections to like the more traditional combinatorics of reduced words, like Stanley symmetric functions, the Edelman-Green algorithm, or anything kind of along those lines?
So Edelman-Green algorithm helps to count average number of SK. So there's some connections, but for not really huge, because I know only about average numbers and Edelman-Green.
I also had a question. So when you're trying to prove the existence of CK, you said it's super additive. So that immediately gives you that they exist by Feketa's lemma. So is the real content that it's finite?
So it's finite, but if it's finite, it's not enough. Yes, we need
all you need is Feketa's lemma. Feketa's lemma says that if you've got a super additive function, that limit exists.
Yes, I think it's probably what we did, but after this step, it's really easy to prove, and it's easier than check all literature.
Uh-huh. Well, it's actually the third, right? The third thing says that it's a super additive function.
Yes.
That once you have that, you're done.
Yes.
Yeah.
Here it's a very standard trick. So, but I don't know where we can find this.
Yeah. Okay. Other questions?
So I have a. Well, perhaps I can ask it afterwards because there's not enough time. But I had a short question.
If it's short, we can do it because it's the next talk is until 35 after the hour.
Oh, okay, it shifted. In that case,
I was confused by that too when I first saw it. But yeah, we still have 4 minutes. So go ahead, Dan. But this will be the last.
There is this probabilistic model of sorting networks, random sorting networks. Does this maximum have a natural interpretation there? Maybe this is a trivial question. I haven't had time to think through it.
But it also gives you just average number, not maximal, unfortunately.
I see. So looking at things that way.
Yes. So because here it's a very special case when you have this maximal number. So in average, it's because it's possible to see in sum of this because this sum is very huge. So this sum is bigger than 12 choose 2. So this sum is not 12 choose 2. So and for average, these numbers will be, some of these numbers will be 12 choose 2, but it's not our case.
Okay, there's another question in the chat, but I think, Gleb, maybe you or Christian can answer that in the chat as well, because we should give people a break before the next talk, which will start very shortly. Actually, there's a couple of more questions in the chat. So let's thank Gleb one more time. The next talk will start in about 3 minutes.
Theo, if you're here, you can maybe try to share it to see if it works.
Okay, let me try to do that. Can you hear me, by the way? Can you hear me well?
Yes. And can you also try to move the slides? Yeah, it works.
Okay, how does it look?
Excellent. And Theo, do you pronounce your last name Duvropoulos or?
That's actually very good. Okay, yeah, I mean,
I play Greek music, so it's not exactly a new thing for me, Greek names.
This is Theo Duvropoulos, and now, like, my official name is Theodosios, and so my thesis had to be published under my official name.
Right.
So sometimes when I reference my thesis, the reviewers get upset because they say, why don't you say Theo? And you say Theodosios, maybe it's another person. So, you know.
Yes. I am blessed with a very simple first name, so I don't need to worry about any problems like that.
If it makes you feel any better, it's the opposite with me. People usually lengthen my name to Daniel.
Oh, and it's supposed to be just Dan?
Yeah, it's just that.
Ah, okay, interesting. All sorts of things. Okay, so this is the last talk for this session, and our speaker is Theo Dovropoulos, who is going to be speaking about Hurwitz numbers for reflection groups. Okay, so Theo, it's all yours.
Okay, that's great. Thank you, Bruce. So thank you, everybody. I'm very happy to be here, even if it has to be online, as the situation is going for the last few years. I have an exciting project to talk to you about. So usually I like things that are particularly nice in the symmetry group, and they have analogs in reflection groups, because I'm a student of Ukrainer, former student. So this is another one of those events, right? So I'm going to talk to you about a version of objects that maybe should be enumerated by an analog of Hurwitz numbers for reflection groups. This is joint work with Alejandro Morales from UMass Amherst as well, and with Joy Lewis from George Washington University. I've been very lucky that they invited me to the project. This is, I think, I'm going to persuade you, a really cool one. So I'm going to spend the first few minutes just giving kind of like an overview of the standard, the usual Hurwitz numbers. So the main combinatorial object that's counted by the Hurwitz numbers is certain factorizations in the symmetry group. So what you're doing is you're factorizing a permutation, but you're only allowing your factors to be transpositions, okay? And then you impose certain conditions on that. What are the conditions? The factorization has to be transitive. Transitive means that the collection of transpositions that you use, it acts transitively on the natural set that the symmetry group acts, right? One way to think about it is that you can model transpositions with edges between their corresponding numbers. And then if the collection of edges that you have is connected, then the group generated by transpositions is all of a sudden, otherwise it would be something smaller. So I have for you two examples, one of a not transitive factorization of this permutation. Right? You see we have two connected components, and another one that is actually transitive. Okay. So the other thing now that can vary is the number of factors that you use. Right? If you fix the number of factors, that corresponds to the genus in some nice surface, and those are the Hurwitz numbers of that genus. So we're going to be interested today mostly about the case where the number of factors that you have is the smallest possible. Right? So the Hurwitz numbers, for us for now, they count factorizations of some permutation sigma that are minimum length, they're transitive, and the factors are only transpositions. Right? So there is a really cool theorem that goes back to Hurwitz in the end of the 19th century. And it says that the number of those things is very nice. It's a nice product formula. So it depends on the cycle type on the permutation, that's reasonable. And check this out. I would like us to remember a few of the important ingredients. So we have a big factorial at the beginning, and even more, the number n plus c minus 2 turns out to be the minimum number of transpositions that are needed. So this is in fact the length of the factorization. Then you have this n to the c minus 3 that should remind you of like counting trees or cacti in a certain sense. And then you have some sort of nice product formula with a lambda i's. The special case of this formula, if you count factorizations of the long cycle, you get n to the n minus 2, which is the number of trees. You count factorizations of the identity. That's important. Even for the identity, the opposite element in a sense, you still get a tree-like factor. And that matters. Trees appear a lot in this concept. And you also have the big factorial. All right. So because I'm going to make a point that this is an interesting generalization that we're given, I want to advertise a little bit the fact that these Hurwitz numbers, they appear in a lot of different areas of math. So I'm gonna provide evidence by saying that look at all these different methods that people have used to prove them. So originally Hurwitz and Strel, they used a combinatorial cut and join recursion. Means when you multiply by a transposition, you're either going to merge two circles or break them apart. So this whole cut and join theory, it kind of like originated in these ideas. Strel filled in some gaps that Hurwitz hadn't really written clearly, and there were serious ones, right? And then Goulden and Jackson, also using the cut and join picture, they used generating functionology to prove the formula. So an important ingredient in that proof was Lagrange inversion techniques. Yes, thank you for answering the question in the chat. So the reason that I mentioned these together is they didn't explain the product structure of the formula. Right? So there is, moreover, a very popular geometric proof. It's a much broader setting where we have an ELSV formula. We have a way to connect the counting of factorizations like this and for higher genus. And this turns out to be a geometric object. This goes down to calculating the degree for an algebraic map that is defined over MGN bar, right? The compactification of the space of curves. And this is a difficult object. And this formula comes out of doing certain natural integrations there, but also you cannot explain the product structure. Now, for us, the most important one is this really cute proof that is kind of a little bit unknown, or maybe not, I don't know, in as many people as I would like. So Sheffer, Pouallon, and Tutsi, they did a really, truly immediate bijective proof of that, right? So they did use the usual card theory or map theory, and they translated the factorization to a collection of objects, and it turns out that you had some reasonable labeling structures for the factorial. And the other factors here, there was some sort of trees on the cycles of the permutation. Maybe we could call them relative trees, they call them cacti. I'm just going to say that, you know, if you're not familiar with that proof, check it out, it's really cool. Otherwise, you have to trust me that there is a nice combinatorial argument in SN where part of this formula is explained by using these objects that relate together the cycles of the permutation, as if they were relative trees. Right. So why do they call them Hurwitz numbers? So again, it was because they started with work of Hurwitz, who was interested, however, in enumerating Riemann surfaces. So in fact, Riemann surfaces were that could be branched over the sphere, and you could have prescribed monotomy around the branch points. So this was really interesting because, you know, this happened before we had the main kind of like modern day topology by Poincaré. This happened before we had representation theory, and a lot of these new ideas of the 20th century appeared at the time. The definition of the braid group as the fundamental group of the configuration space of points that Sarah was talking about before. A lot of these things or go back at least partially to this really cool work of Hurwitz. Okay, so we're going to be interested in the genus zero case. I'm going to disappoint you if you ask me at the end whether we have a similar picture for reflection groups. I think right now we don't have the technology, but it's a really good question. If you have any ideas about that, we should talk about it. All right. So now I want to kind of like start setting up some material to be able to state the theory. So it's going to be a little bit dense because this project turned out to kind of like blow up. It needed quite a lot of theory builds. In fact, we ended up breaking it into 3 papers. But I think I'm going to give you the basic ingredients. So we're going to change our ambient group. Instead of the symmetric group, we're going to have a veil group. And in fact, our theorem calls for all well-generated complex reflection groups, but I'm barely going to talk about it at the end. It's just it becomes more complicated. So for now, just veil groups. The property definition, before we had that a factorization has to be transitive, as much as the transpositions have to act transitively on the numbers 1 to n. Now, this is a really cool property that does not have an analog for reflection groups. There isn't a natural collection of points or numbers on which a reflection group is acting. So this property is going to be very important for us. We're going to change it, and we're going to say that a factorization is going to be called full if the factors generate the whole group. It's equivalent with being transitive in the symmetric group, and it makes sense in arbitrary reflection groups. And it turns out to be good because it gives us nice structural properties and nice formulas. And we have to thank Gil Sefer. Gil was the one who suggested to Joel and Alejandro, who were working on similar problems, whether they could test this property for the identity for all elements, and eventually enter the project as well. Now, we're not going to be able to give a counting formula for arbitrary elements in the groups. We're going to be giving them for parabolic quasi-Coxeter elements. Just keep in mind that these contain all of the elements in the symmetric group. These also contain all of the parabolic Coxeter elements, so it's a big enough family. The definition is that an element is called parabolic quasi-Coxeter if it has a reflection factorization that's kind of tight. that if it is of minimum length, the factors generate a parabolic subgroup. Right? This also has to do, this also has interactions with the root lattice, but let's keep it like that. And let's keep in mind that it's a big enough class of elements. An important object that appears here that generalizes this idea that I was talking about, connecting the cycles of the permutation with a relative tree. This is a relative generating set of reflections. So you start with your permutation sigma, or with your element sigma, and you consider sets of reflections that if you add them to a reduced factorization of sigma, you get a collection that generates the whole group. So they're relative generating sets because they also need a reflection factorization of sigma to become truly generating sets. Now, keep in mind, you can always add a bunch of reflections and generate the whole group, but I'm imposing a condition that has to do with length. I'm saying that I'm allowed to add only n minus the reflection length of the element. So some elements do not have relative generating sets. And it turns out that it is exactly the parabolic Pascal-Coxeter elements that do have relative generating sets. All right? Just keep in mind for a bit that there is this nice compatibility because our class of function and this new object that are like relative trees that are relative generating sets. Okay, so now I'm ready to show you our theory. I'm going to use two notations. F full of sigma is the number of shortest length full factorizations, where the factors generate the whole group. And F red of sigma is the number of reduced of shortest length factorizations that don't necessarily generate the whole group. So our theorem is a formula for the full factorizations of sigma that does involve all these objects we talked about. So the relative generating sets and the reduced factorizations. Now, you might be upset with me and tell me, Theo, you're using this other thing that you haven't said anything about, that it might be unknown as well. Well, it turns out that for the parabolic Pascal-Coxeter elements, these behave very well. These have very nice product formulas. We still don't understand them too well, but in the parabolic Coxeter case, we understand them completely. More generally, we have some conjectures, but these behave well. So you should think of these as part of the product formula. Okay. So I'm going to give you here the correspondence between the main ingredients of the two formulas. You see we have the factorial that appears in both of them. We have these relative generating sets that I'm telling you somehow have to do with the n to the c minus 3 factor. I'm going to explain it in the next slide. And we have a bunch of reduced factorizations that in the symmetric group are really related to these expressions. So in fact, I would like to write it down just so that for the experts, they can see exactly what this is. So we have the lambda i's to the minus 2 here, and lambda i's minus 1 factorial is the length. Now the connection index for the symmetric group for a Young subgroup, that's the product of the lambda i's. For the whole group is just going to be n. This is just n plus c minus 2 factorial. And it turns out that the relative generating sets have this nice expression n to the c minus 2 times the product of the lambda i's. So you can easily see that there is a little bit of spreading of the lambda i's around, but the main ingredients are there. Now, I want to point out, somehow, magically, the connection index appears there. So the connection index, it's an important invariant for Veil groups and has to do with the root lattice and the weight lattice, but it also has to do with the Gramian determinant of root vectors. It has something intrinsic to do with collections of reflections that generate the whole group, because these things give you basis for the root lattice and similarly basis for the co-root lattice, and somehow the numerology matches. We don't understand it very well, but it is clear, or hopefully it will become clear, that it's an important ingredient because it appears in the complex case as well. Right. So hopefully I persuaded you that this is truly a generalization of the standard formula. I want to show you this very cool symmetric group argument, which completes the fact that our version of the formula and the standard version of the formula is the same, and there is a reason for that. So if you cancel out everything, the thing that you need to prove is that the relative generating sets for a permutation of psychotype lambda are enumerated by this expression, n to the c minus 2 times the product of the lambda i's. But how many ways can you create relative trees? You have a cycle here and another cycle. And to create a relative generating set, you have to add some transpositions that make the whole thing a tree, right? So you have to add a tree on the cycles. But for each edge of the tree, you have many options. You can pick whichever of the lambda I numbers here with whichever of the lambda j numbers here. So for each edge, you have lambda I times lambda j options. So if you put them all together, you're summing over the trees on the cycles, and the quantity that you're using is the product of the lambda i's to the degree of that vertex. Now, this immediately becomes by Cayley's theorem, by Cayley's weighted theorem, the expression that we want, right? So the sum of the lambda is just n, and this is the reason for n to the c minus 2. This is a way to count cacti, but I really like this because the same calculation appears in this sort of permutahedra Erhard polynomial structure that recently has become very popular, right? So it's similar things that happen there. So it's kind of like an intrinsic thing. Okay, so a few things about our proof. It has a serious disadvantage, as many of the proofs in this, many of the first proofs of cool theorems for reflection groups have. The disadvantage is that it depends on the classification. So the classification, the Weyl groups and the reflection groups are classified, and we did it case by case. So we calculated both sides of the equation separately, and we compared them, and voila, they're the same. For the combinatorial families, the right-hand side is essentially combinatorial arguments because these families, they're generating sets, they behave like trees. It's similar. And for the left-hand side, we related the full factorizations in these groups with the full factorizations in SM. I have to point out, this is one of those things that is natural when you hear about it. It's pretty tricky. It's quite technically complicated. And when one faces a situation like that, one of the best solutions is to have Joel Lewis in your group, because Joel is really great with these things. So he developed this really nice approach to kind of like characterize the situations that appear and complete the numerology. And for the exceptional groups, we counted again both sides, used computer calculations. For the left side, we used the Frobenius from presentation theory and some Möbius inversion. And the right-hand side is kind of like straightforward. So it's an ugly proof, but a great theory. So, I wanted to point out a few heuristics. So I hope Igor, if he's here, we're not going to hate me because these ones do not work. So it's not as if I'm treating you on anything. I'm just going to point out that there is some compatibility between the combinatorial objects that appear. So here we have something that has to do with reduced factorizations of our element. And here we have something that has to do with completing the necessary reflections to generate the whole group. If you put these objects together, voila, you have a full factorization. So you start with the factorization of your element, and then you pick each of the reflections in the relative set, and you use each of them twice. So then the product, you know, it remains the same. And because you have used all of the reflections in a relative generating set, you have a full factorization. And, you know, I mean, it's a good numerology. Here we have Fred many ways to do it. Here we have RGS many ways to do it. And maybe there would be a Saflin or something like that. Well, you know what? It doesn't work. At least it doesn't work in the obvious way that we thought about it. But it's kind of like, it's right there, right? There might be something behind it. In particular, there might be a complicated way to start with factorizations like that, spread them around, change the factors so that they're not really, you know, reduced factorizations here, but do it in a controlled way. The evidence that exists for that is that the whole collection of full factorizations of sigma is in a single Hurwitz orbit. Hurwitz orbit in the sense of the braid group action on tuples of elements. Right? So we hope that this would be an approach that could give us something in the future. Now, I'm sorry, I'm going a little bit faster. There's so many things here that I'm excited about. I think it's a really good project. Some of the side scenes that appeared, or kind of like we hope are important contributions as well, are the following. So I mentioned in my formula these Fred numbers, which is the numbers of reduced factorizations of these things that appeared. And those were kind of like generalizing the lambda i's to the lambda i's that appeared in the symmetry group case. So I mentioned that for all of the classical star elements, these things are always very nice. And this is a sort of discussion of why these are so nice. So for Coxeter elements or parabolic Coxeter elements, this is a known formula that goes back to Lihenga and Arnault, and eventually was advertised more by the Cis and Sapoton. It has to do with the number of maximal chains in the non-crossing lattice. It is this interesting chain number h to the n times n factorial of the size of W. H is the Coxeter number of the group. But even if it's not a Coxeter element, I'm giving you here the table of all of the quasi-Coxeter elements in the real reflection groups. All of them, they're products of small primes. Now, this observation, it goes back to Voigt, who was a student of Briscoe, but to me, it was first mentioned by Christian Stum, who did computer experiments and found out that there is a really nice structure here. So I tried a lot to figure out an explanation for that. And at some point, I had this really cool conjecture, but it's been on hold for a while. So it involves this more difficult geometric object that's analogous to the Liasko-Lihenga morphism that appeared in the ELSV formula, also in the Sis's work. And so there is a geometric object that's called the Frobenius manifold that's associated with Coxeter elements, and a degree of amorphism there turns out to be equal to these enumerations. So all of the times for all of the Frobenius manifolds where we know all of this data, it turns out that this sort of conjecture is true. I don't have a good way to explain it, but I feel it is compatible with previous theory. And this also comes with a dual braid theory. So Baumeister and Ries, they developed a way to do presentations for the group just by using the reflection factorizations of quasi-Coxeter elements. So if you're an expert of dual braid things, this would sound natural to you, but it's interesting, right? So these give presentations of the Coxeter group, not of the braid group, but they do give presentations of something else, possibly the complement of some other discriminant. So cool stuff for the quasi-Coxeter elements. Now for the complex, do I have another 4 minutes? Is that it?
Yeah, 3 minutes.
So for the complex reflection groups, just briefly, this is the real theorem, right? The real theorem holds in high generality. For all complex reflection groups that are well generated anyway, we can give a formula for the full factorizations of quasi-Coxeter elements. It doesn't look as good because this first formula has a product structure in a sense, even if this object is a little bit weird. The true formula has this object becoming a summation. So instead of just adding, the index of one group over another, for each element, for each relative generating set, we calculate the quotient of two Gramian determinants. Now for expert, it's clear that the connection index can be realized as a Gramian determinant with associated roots. But in complex reflection groups, these Gramian determinants are complex numbers. They're not integers. And somehow magically, when you add them together, they become integers and they count something. This is remarkable. And it's even more remarkable because it's not an accident. These things have appeared before. So Breker and Michel, they managed to define good analogs of root systems for complex reflection groups. And in those analogs, exactly these Gramian determinants play the role of the connection index. It wasn't a complex number, but it was the idea that was generated by this Gramian determinant in an extension of the rationals, but it was meaningful. And so the same kind of like numerical quantity magically counts factorizations here. So I feel there's something that truly involves the behavior in a lattice and the core lattice, but we still don't understand. So I'll say one final thing. A reasonable question is, what can we say about the higher genus case? The LSV formula in particular tells us something about arbitrary genus factorizations. So we don't have formulas, but we have observed a really good structure for the generating functions. So here we have the generating function where we take arbitrary length full factorizations of a fixed permutation. So, the generating function is with respect to the number of factors. We're not changing the group at all. This is an important distinction to previous work. And it turns out that these sort of generating functions, they always have nice formulas, nice expressions. They're always a finite sum of exponentials. And it turns out that you can predict a few things about them. There is a factor that involves the length of an element. There is a factor that involves the number of hyperplanes, and there is a polynomial that looks really cool. So this is part of the modeling, let's say, of the expression of the generating function, and it's characterized by this polynomial. And these polynomials are often unimodal. They always have integer coefficients, but sometimes the coefficients can be negative. So this is the cyclic group of order 6. So as we're talking about these things, Alejandro had this amazing idea to just plot the roots of these polynomials. And these things look amazing. It's just ridiculous. So they're very rigid. These are in the appendix of our paper. It's going to show you those that look a little bit nicer. So look at that. These are roots of a polynomial, of polynomials that encode the number of full factorizations of elements in these groups, of the identity in each of these groups. Look at the structure of these things. It's remarkable.
So,
anyway,
Theo,
yes.
your time is up, so you should bring it to close soon.
This is it. This is the final thing that I wanted to say. So I had another thing about the homogeneous case, but I just wanted to point out the nice product structure of these generating functions. Anyway, so we have broken it into 3 parts. The first one is on the archive, and the other ones are coming soon. Thank you very much. Have a happy 20.
Thanks so much for a lovely talk. And are there any questions? Actually, there was a question in the chat. It says, what are the advantages of using Sage for your calculations as opposed to, for instance, Maple or Magma?
I mean, a big part of it is just that we're more comfortable with Sage. Sage also connects different programming environments. In particular, Sage plays very well with GAP, and GAP has a good structural presentation for complex reflection groups as permutation groups. So through Sage and GAP, and the work of Jean-Michel and Sevi and other people, you can do very easy character calculations, which is what we needed to do for one part of the project. Also, Sage is open source.
Open source, yeah. It seems to become the standard for doing combinatorics, at least. Are there other questions?
I have a quick question. Do you suspect any relation to integrable hierarchies, partial differential equations, anything along those lines?
So that's a good question. This is one of those things that does in fact appear. I couldn't put it in. The idea of the cut and join equation is fundamental, right? And it's natural. It just says you have an element, you multiply with transposition, what happens to it? You can ask the same thing here. You have an element, you multiply with a reflection, what happens to it? It turns out you can get the recursion in a good way, like the things that will appear if you test this formula are going to be smaller parabolics or elements of higher length. So you can do the recursion part, but to do the hierarchy or to even do the differential equation, that's a little bit tricky because one advantage that is hidden in the Gould traction approach is that you have a variable for its cycle length, essentially. Well, in this situation, you can have quasi-Coxeter elements or Coxeter elements that have the same length but are of different type. So you would have to have like a fake variable for each type of those, and it's unlikely that something would behave very well, at least not easily. So I'm not sure.
Other questions? Okay, well, let's thank Theo again for a lovely talk. And this concludes the session. Dan, did you have any other, are there any announcements or are we done?
No, I will stop the recording now. Well, actually, so for those of you who want to stay